So we're going to look, the main idea today, we're going to look at the derivative and then f of x as well, the function and its derivative. And we're going to look at the graph of f prime of x now. So that can get a little confusing, right? We said something like, you know, if my function, I'll keep it simple, is x squared, I can graph that function. And that would be where all these y values represent my y value of that function. Then I can take the derivative using power rule and get 2x. And that's a function itself. So if we just graph that as a function. So today we're going to be looking a little bit at the derivative as its own function. Not really like, I mean, we are still thinking of it as the slope of the tangent line on f. But we are going to go ahead and graph that function on its own. And now the y value on this graph would represent the derivative. So in other words, on 2x, if I look at the x value 4, it's going to have, if I plug 4 into the derivative, it's going to have a y value of 8. So what does that mean? It means that f prime of 4 equals 8. So these y values on this derivative graph still represent the slope. So what that means is on f, if I go over to 4 and I draw that tangent line, it's going to have a slope of positive 8. So remember, the y value here just kind of means the slope back over here, but we're going to look at f prime of x as its own function. I want to talk about the characteristics of f prime and what that tells us about f and vice versa. So here's the kind of rules. If the derivative is equal to 0, then we know the original function f has a horizontal tangent line. Now, just because we looked at the end of the last video, just because it's horizontal, it may or it may not produce a relative max or a relative min. So just because the derivative is 0, f may not have may or may not have a max or a min at that spot. We saw a point of inflection the other day on that. Well, I'm not gonna. Whoops, sorry. I'm not gonna recap the video. I'm just gonna keep going. I'm not gonna talk about yesterday's. So the derivative, when the derivative is bigger than 0, remember this means that it's positive. Then we know f of x is increasing. I think of the derivative as a rate of change in this example. The example that I like, or that I use, is that if the derivative is positive, that means it's a rate of change. So if you think of the temperature outside, if I say the rate of change, or the derivative of the temperature, is positive, that means the temperature itself, right, the original function, is increasing. Temperature is going up. So that's how I think of that one. And vice versa works, by the way. If I know the temperature is increasing, then I know the rate of change of the temperature is positive. So now if the derivative is negative, that would mean my quantity. So if my rate of change is negative, then my original quantity is going down. Now this helps us, these two kind of go back to when it's 0. It can tell us if there's a max or a min there. So if my derivative changes from positive to negative, so remember what that means is the function was increasing because the derivative was positive. Then it switches over where the function switches over to where the function is now decreasing, because on the other side of an x value, it's now negative. That means if a function was increasing, then switches at a point and starts decreasing, that means that you have a relative maximum. Okay, and these are typically on intervals. Over a whole bunch of x's, it's increasing or decreasing. This typically happens at a single Let me try this again. Now, what I mean by a single x value, it might happen more than once on a graph, but it's not over an interval. There could be 3 or 4 different places. So these also are when that occurs, right? When it's 0, now I can tell if it's a relative max or a relative min. So I won't write that out, but since they both originate from this, those happen. They both originate from this. When the derivative is equal to 0, they will happen at a single x value. So now if the derivative changes from negative to positive, that means f was decreasing, because negative means decreasing. Then it switches to increasing. That means, I'll leave that picture there, has a relative minimum. All right, so let's look at a graph here. This is our graph of f of x. And they want us to draw a possible graph of f prime. So the first thing that I always do is I try to identify any spots where the derivative could equal 0, any x values for which the derivative equals 0. Derivative is 0 when we have a horizontal tangent line. Looks like it happens at -4, 1, 2, 3, 4, and 5. So I know if I'm going to graph my derivative over here, remember that my y-axis is now my values of my derivative, which are the slopes of my tangent lines. So I know that the derivative is 0 at -4. So when I put a point there, it means the derivative is 0 because my y value on this graph is 0. It's 0 again at 1. And it's 0 again at 5. Now I'm going to use this stuff backwards. Oops. So this is a relative max. The function was increasing and now switches to decreasing at it. So the derivative must have been positive and then switches over to negative. So I'm going to draw a little slash there like that, because above the x-axis means positive derivatives, and any y values below are negative, right? And remember, the y value represents the derivative. So that's a switch from positive to negative on the derivative. And on the function, we know it's switching from increasing to decreasing. So here at this 0, it's switching from decreasing to increasing, which means the derivative went from negative to positive. Then over here at this 0, it went from increasing back down to decreasing. So the derivative switched from positive down to negative. Okay, so this, by the way, is a polynomial. I know that just because it's continuous. It's a smooth curve with a couple of turns, which means it's x to some power. So I know that this one is also the derivative, just by what I know about power rule, is also going to produce a polynomial, and it's just going to have one less power, which means one less turn, possibly one less x-intercept, right? This had 4 x-intercepts. Mine will have 3 typically. Doesn't have to. So anyway, if I know it's a polynomial, I'm just going to sketch it in now. Here I have a turn where it comes back up and around, and then it comes back down. So that is a possible sketch of my derivative. I don't know like how far down it comes. Maybe I should have kind of angled it more and come down this far, but that we don't have to worry about that. We're worried about a couple of things. Did we get the correct points where the derivative is equal to 0? And on our intervals, is the function positive when it needs to be and negative when it needs to be? So on this interval here that I highlight, which is from -4 to 1, it looks like the graph is below the x-axis. That means that f prime of x is less than 0, or the derivative is negative. That means on that same interval, -4 to 1, my function should be decreasing, which it is. So that's the other thing to note. Any spots where the function's decreasing, the derivative must be below the x-axis. I'll do them in different colors each section. So let's go with blue. Here the function's increasing from left to right all the way up to -4. So that means my derivative must be above or positive above the x-axis. It is. Let's look at another section. We'll go orange. The function from 1 to 5 is increasing, which means my derivative from 1 to 5 must be above the x-axis. My derivative must be positive because that's when the function's increasing. And then lastly, we can leave it in green over here. Because my derivative, I'll go backwards, because my derivative is below the x-axis, that means that it's negative. The function must be decreasing on that interval from 5 to infinity, which it is. All right, so again, we're now looking at the derivative as a function itself, and we're graphing that function. Hey, it's 9:41 a.m. again. I got to fix my iPad. All right, so we're going to do both of those things. So pictured below is the graph of a function of f. We want to answer questions about f prime. So this is f of x. All right, so approximate the value of f prime of 4. So if I want to approximate the derivative, first of all, f prime of 4, 1, 2, 3, 4, it's like somewhere around here. I want to approximate the slope of that tangent line. The way we can do that is we can do the secant line of 1x value below and 1x value above 4. So we can do the slope of that secant line. So if they want the value of the derivative or the slope of that line at 4, I'm going to do the slope with x values 3 and x values 5. So it looks like 3 has a y value of -1. And then 5 has an x value of 4. So to do an approximation of the derivative at 4, approximation means a secant line. Right? If I want the exact derivative, I'll just do power rule, or I could do the limit process with the secant, the definition. So my approximation, so I want to make sure I use an approximate sign, and then I can do slope between those 2 points. So I've got -1 minus 4 divided by 3 minus 5 to find that slope. I get -5 over -2, which simplifies to 5 halves. I should probably use approximate signs. Okay, or you can say 2.5. At what value of x is the derivative equal to 0? Justify your answer. Now remember, this is a graph of f, and they're asking about f prime now. So that's what we're trying to get at in this lesson. So the derivative is 0 anywhere that I can draw a horizontal tangent line, and those typically occur on polynomials at maximums and minimums. Hi. So I can say that, restate the problem, or the question. The derivative equals 0 when x equals -4, x equals 1, and x equals 5, because, and then give your justification. So I restate the question, answer the question, give my justification. Because the graph of f of x has horizontal tangent lines, that's how I know the derivative is 0. Because derivative is slope of the tangent line. Horizontal tangent lines have a derivative of 0. On what open interval is the derivative less than 0? So now they're asking, if I know f, where would the derivative be negative? Well, the derivative is negative on any intervals where f is decreasing. So there's 2 times where that occurs. From, what is that, -4 to 1, the function's decreasing. And then again from 5 to infinity. So on these 2 intervals, -4 to 1, and then 5 to infinity, that's where the function is decreasing. Therefore, f prime must be less than 0 or negative. So we're going to say f prime of x is less than 0. on the interval. We never include the endpoints on these, increasing or decreasing. On what intervals is the derivative positive? Oh, and by the way, so I know I restated, I answered, and then I gave my reasoning. So vice versa is going to be true for positive. I'll trace them in green. The function's increasing from negative infinity up until negative 4, and then it's increasing again from 1 until 5. So I'm going to say that f prime of x is bigger than 0 or positive on the interval, what was it? Negative infinity to negative 4, and then union 1 to 5, because the graph of f is increasing. At what values of x does the graph of f prime of x go from being below, which is negative, to above the x-axis, which is positive? Justify your answer. So f prime of x will switch from below to above. Now this is going to occur at certain x values, at x equals. Well, above to below means the function was increasing, right? If the derivative is above, derivative is positive, and then switches to negative, that means it's where the function, at any x values where this function switches from increasing to decreasing. Right? Oh no, sorry, below to above means we're going from decreasing to increasing. So if the derivative was below, it was negative, the function's decreasing, then it switches to increasing. It's going to happen right there at that x value of 1, at x equals 1. And then we want to say why, because f of x has a relative minimum Okay. Sometimes I can pause the video, other times I cannot. Period 1 is starting. I can't pause this video, so I'm going to, or this recording, I'm going to stop it and do a part 2.